So, hello everybody. I'm sorry I couldn't do this, and all the troubles I had joining the workshop. Anyway, I hope this kind of makes up for it, and I can do this brief presentation I have prepared that my Miss Laf asked me to do about our experience here in the University of Minho. Working with non-destructive techniques, particularly focused when we try to do a structural analysis of heritage buildings. So here is some images of us working in the on-site. This is the type of work we do in several locations. In this precise case, we are doing sonic tests in different structures. And despite we can see a lot of works dealing with non-destructive techniques in the literature, in academic works, I believe this their use is still not widespread among professionals. So we believe that there is a necessity to create awareness about the usefulness and the great value that these techniques have when dealing with heritage structures. Because in the end, this is the only way that we can obtain and extract information from the structure without doing any damage to it. For example, in this case, if we use georadar or GPR investigations, we can detect hidden information about the geometry or the construction of a monument. Or, for example, through dynamic identification test, we can have an initial understanding of the structural behavior of a building. Or as some of you already highlighted during this workshop, if we use flat jack or another kind of techniques, we can even get an approximation of an estimation of the material properties of the structure. We know that flat jack is not really a non-destructive, but is really minor, the damage that we do in the structure, and is easily repairable. Moreover, there is another, as we can see later, another techniques like the sonic testing that we can also extract, and that one is completely non-destructive. So the idea of this presentation is to show the common workflow that we used at the University of Minho. Is the workflow that we show to students in our masters. It's also the workshop that we do for the consultancy works that we do, and I will show you a little bit this workflow with some case studies that we have done in the past. First of all, one thing that I think is important to highlight is that non-destructive techniques are always a complementary tool. So it's not, even though if they can have a value by their own, we should always do them with another set of tasks that will help us to understand much better the results that we will obtain with them. So in this particular case, as an illustration of what I mean, is that before doing any non-destructive testing, we had available these detailed archaeological studies that allowed to distinguish the different construction phases of the building, and even to determine some possible construction joints from that belong to different because these parts of the walls were constructed at different eras. At the end, these joints were structural, and we could, when we did the dynamic identification test, we could figure out that these joints had an important influence on the structural behavior of this castle. Then when we prepare the numerical model and we perform a model analysis, we had to take into account these joints to simulate properly the real behavior. If we didn't have these archaeological studies or these previous archaeological studies, this behavior will be much more difficult to replicate. And at the end, what we have is a numerical model that we know might represent in a more reliable way the real behavior of the structure. So besides historical research, also we try to perform always some detailed geometrical studies using photogrammetry or laser scan or any other techniques that are available. In this case, for example, this is in the sanctuary of Santa Lucia in Portugal. So we perform also photogrammetry, an external photogrammetry using drone, and internal photogrammetry using our cameras. And at the end, what we get is a new set of plans and a detailed 3D model of the structure that gave us very important information, either to create our 3D models, or also we get information that is more difficult to obtain accurate thickness of the different elements, and other very useful information that we need to obtain before we carry out any kind of structural analysis. But anyway, as I was trying to explain before, this information can always be enhanced if we use some of the non-destructive techniques that we have available. So, for example, when we did the photogrammetry, in the case of this dome, we only had information from the interior. So we cannot know what is the thickness, for example, of this dome. So we can use another techniques that provide us this information, such as GPR. And in this case, it proved to be particularly useful because, in spite of what we were thinking, that it will be a stone masonry dome as all the rest of the building, it was actually a very thin shell of less than 10 centimeters, and it was actually reinforced. So we found out that actually this dome was made of reinforced concrete. So again, I guess all these techniques fit each other. Ultimately, what we obtain is an accurate 3D model that we can perform any kind of operation and analysis, such as study the deformations of the towers, which in this case was important for us, or we can do a structural analysis. Always knowing that what we are doing can simulate or is reliable, and it represents well the real structure. This is in essence, this is the essential workflow that we try to follow in our works when we aim to do some advanced structural analysis of heritage buildings. At least we always try to do these sonic tests, because this is our a kind of fast and direct tool to have a first estimation of the material properties, and it's non-destructive completely. And at least we try to do always a dynamic identification test to obtain a first estimation of the modes of vibration of the building, so we can calibrate our numerical models. Again, just to emphasize that all these previous works that we can do are really helpful and can highly strengthen the confidence that we have in our final numerical model, or the historical survey, the detailed geometrical surveys, or GPR, Impact Echo, any other technique that we have available. Just an illustration to the workflow from as I was describing before. This is the case of the Shah Mosque in Isfahan. So here we did the essential three-step workflow that I was discussing before. So first we did some sonic tests on all the structural elements, such as the domes and the walls of the mosque. In the sonic test, for those of you that are not familiar, at the end the physical principle of the test is that the velocity of the waves that propagates through a material are directly correlated with the elastic material properties, such as the Young's modulus. So at the end, what we do in the test is we generate a wave, we measure the traveling time of the wave, and then we compute the velocity of this wave, and then we can use it to estimate the Young modulus, as this is the case. So we can have a first estimation of the Young modulus of the brick masonry that was used in this structure. Then we can do the dynamic identification test. So we put our accelerometers in places where we believe that will be excited by ambient vibration, and then we can obtain the natural modes structure. Once we have this information, we can prepare our numerical model. The first input we have is the material properties that we obtain through the sonic test, and then we can perform a model analysis and try to compare if our numerical mode shapes correlate well with the experimental ones. If they not, we can do this calibration process, which will be to update vary slightly the material properties, vary the boundary conditions until we obtain this good calibration, and then we can be more or less quite certain that our model will be simulating well the real structure, so we can proceed with the structural analysis. In this case, for example, this is the seismic analysis and a pushover we did in different directions of the mosque. And finally, the other thing I would like to discuss to talk to you about is how we can also use non-destructive testing for different for a different scale. When we do, for example, a large-scale seismic vulnerability assessment of an old historical city center. No, this is in this case we also believe that destructive testing can be very helpful, and because especially when we are dealing with typology that is recurrent, that we can find a lot of examples of that very similar typology within a given area. So then we can perform this non-destructive testing. And essentially what we do is we try to explore the development of a probabilistic methodology that will allow us to derive analytically some seismic fragility functions that includes uncertainty regarding different parameters, such as the material mechanical properties. When we try to do these probabilistic methodologies, what we need to define is a probabilistic distribution of the parameters selected. So if we want one of the parameters that we want to study is the material properties, we need to find what is the most adequate probabilistic distribution. In this case, there is some codes, such as this Italian guide, that give us a prior probabilistic distribution for the different material parameters according to the Masonry typology. But if we are able to perform some non-sonic testing, for example, that provide us also an estimation of the Young's modulus, and we can perform in several number of cases, for example, within a city center of the same typology, then maybe we can obtain a much more specific probabilistic distribution that represents better the Masonry typology of that specific area. Once we have this probabilistic distribution that represents well the Masonry of the area that we are studying, we can perform numerical finite element analysis, for example, to evaluate the seismic capacity of the buildings according to the variation of different parameters that we have selected, such material properties or other construction parameters. For example, the lack of a diaphragm or the presence of this diaphragm. No? As a result, we can construct fragility curves for a given construction typology that takes into account the uncertainty of these parameters, material and constructive ones, which were refined and investigated with the use of non-destructive tests. Eventually, what we can do with this kind of approach is to perform regression analysis and obtain empirical expressions which allow to derive these fragility curves for a given typology without a numerical analysis, which is an easy and fast way to do it for large groups of buildings, since numerical analysis is a more demanding and time-consuming tool. But well, this is more or less what I wanted to discuss. I hope I could give a quick glimpse of how we use the non-destructive techniques in the university, in our group, and to show how vital and fundamental they are for us in all our works. So thank you for your attention.
So now the next presentation is by Marco. Marco, are you here?
Yes, I am.
Okay, I will just have a short introduction by of you. So Marco is a postdoc student at University of Minho. He is originally from Italy and was studying in University of Calabria. And I'm really waiting for his presentation to see interesting stuff he's doing because he's doing a lot of really innovative and he's using emerging technologies such as 3D laser scanners, digital photography, and all of the other technologies in the assessment procedure and in modeling of masonry structure. And he's also a NATA expert, so he's just a few months in Portugal, but he knows how to prepare really good NATA. I hope this is still a fact, Marco. So the floor is yours. I'm looking forward to your presentation.
Okay, can you see my screen?
Just a second. Yes, we see it.
Nice, okay. Mislav, thank you very much for your nice introduction, in particular for the NATA. And so basically I will present in this context just something about my recent works using the visual programming for the structural assessment of historic masonry structures. At first, just a brief introduction about myself. I obtained my master's degree in building architectural engineering in 2015, 5 years ago, with a thesis about the three-dimensional survey and the seismic vulnerability assessment of a built cultural heritage. Then I got my PhD in the same university at University of Calabria last year with a thesis about the development of advanced numerical model to predict fast crack propagation in layer structure and bidimensional media. And since last September, I am a postdoctoral researcher in the research group led by Professor Paolo Lorenzo at University of Minho. Okay, let's start. This is just the outline of my presentation. At first, a brief introduction about the seismic performance of masonry structures, as well as the analysis method that normally we can use. Then I will present the proposed method, which is implemented in a visual programming environment. Moving on, just some results. And finally, I would like to discuss with you some ongoing works and conclusions. Okay, guys, as you know, masonry structures present a very weak seismic performance because they are sometimes made with very poor materials, and normally the connections of the walls are not enough to guarantee a box behavior. So when a seismic event happens, like the case of Amatrice in Italy, entire villages could collapse, generating a loss of life, loss of our identity, and also of our culture. So it's very important to evaluate the seismic vulnerability of these structures, of the masonry structure, before their collapse, hopefully, in a very quick way. To do that, today, structural engineers can use different kinds of analysis methods. I like to classify them in a very simple way. We have those based on the incremental iterative analysis, which are mainly devoted to evaluate the global behavior of structures. And normally they are implemented in a very sophisticated computer software. And in order to solve the governing equation of the structural problem, we also need a very sophisticated numerical scheme to solve the equation of the structural problem as well. Then we have also other methods based on theorems of the limit analysis. Normally they are devoted to analyze local failure mechanism. And in these frameworks, the calculation can be done in a very simple way, also by using end calculation or other kind of very simple analytical tool. But the question now is, what do we have to use? So the choice, to be honest, depends by several factors, like, for example, the cost, the time, and also the knowledge level that we have about the investigated structure. And we have also to say that neglect the global behavior of focusing just about the local failure mechanism could bring to erroneous evaluation of the seismic performance of the structure. To this end, I developed this kind of two-step analysis. As you can see, it is based on two main phases. We have the blue blocks, which aims to assess the global behavior of the structure by performing just a pushover analysis. And then we have the orange box, which is all integrated in a visual programming environment, in particular in Grasshopper for Rhino 3D, which aims to perform local analysis by combining both theorem of plasticity, in particular upper bound theorem of the plasticity, and evolutionary solver. In particular, I used genetic algorithm. As you can see, the link between these two phases is the construction of this kind of control surface, which allow us to coarsely identify the macro block geometry that are going to collapse for that loading condition. What is the control surface? So, as you know, the pushover method is very sensitive to the choice of the control point. And to overcome this problem, I consider several control points on the top of the structure, as you can see in this picture. And the control surfaces is just generated by interpolating with a surface the point cloud, which has as x and y coordinates the same coordinate of the control points, whereas the z coordinate is directly proportional to the horizontal displacement occurred during the step-by-step global analysis. This just means that when we have zero horizontal force and of course also zero horizontal displacement as well, the control surface is basically flat. Whereas in this picture, I'm reporting a control surface where the structure is very close to the collapse time. Okay, guys, I hope that it's quite intuitive that the region of the control surface which present an higher value in terms of slope are those in which the plasticity are concentrated. So the control surface allows the script to identify the weak region of the structure and then to introduce the failure surfaces in order to start the local analysis of the failure mechanism. About the second part of the proposed procedure, it is all integrated in a Grasshopper for Rhino. It is clustered, as you can see, in several groups, which are demanded to perform specific operations. Let's start. The first group is the red cluster, which is demanded to define this kind of control surface generation just by using the data arising from the global pushover analysis. Then we have the second cluster, which aims to identify the sidewall involving in the collapse mechanism. Then we have to define the failure surfaces, which generate the definition of the macro blocks. And as you can see in this kind of cluster, we have some sliders, this one, which are able to define the genetic panorama, and they represent just the variables of our optimization problem that will be performed with genetic algorithm. Then we have the fourth cluster, which allows us to define the frictional resistance of the sidewalls. As you can see in this framework, the user can also change the friction coefficient and also other parameters for the optimization problem. The yellow cluster is devoted to compute the inertial forces, which are very important in order to define the equation of the principle of the virtual works that, as you can see, allow us to compute the kinematic collapse multiplier. This is the orange box is just the box demanded to optimize the problem to find the minimum load multiplier and to find of course, also the horizontal acceleration needed for the activation of the local mechanism. In this slide, I'm reporting just some results. On the left of the screen, you can see basically the flow chart of the proposed procedure. So at first, just a global analysis by using, in this case, I used Abacus, but other kind of user can use different kind of software, of course. Based on the result arising from this global analysis, we can construct the control surface, which allows us to define this macro block geometry. And then, thanks to genetic algorithm, we can optimize to minimize the value of the load multiplier and find the minimum load multiplier according with the upper bound limit theorem. Since a couple of months, I'm also working in collaboration with Dr. Mehrotra from University of Minho, my same university. We are trying to implement my method of analysis with R tools for the rocking dynamic analysis. Basically, starting from the geometry and also from some mechanical data, it is able, this script is able to define the geometry of the macro blocks by using the procedure that I described before. And then the second part of the scripts is able to compute, to define the kinematic constant, to write the equation of the motion, and to provide us a representative time history of the structure of the problem. Another ongoing work is the definition of a grasshopper script for the computation of the horizontal thrust of masonry domes. This work is in collaboration with Dr. Luis Carlos Silva, with Professor Paulo Lorenzo, Daniel Oliveira, and Lamu Musavian from the University of Naples. To do that, we choose to investigate one of the most critical cupola in the world, probably, which is the St. Peter domes, designed by Michelangelo and Giacomo della Porta. As you know, masonry domes tend to generate meridian crack, so the structural behavior of this kind of historical dome is that of a pushing dome, so we can study just a slide of the cupola. In this slide, I'm representing the flowchart of the proposed script. At first, we can parametric modeling the geometry of the dome. Then we have just to set the specific weight in order to compute the inertial force. Then we have just to define the parametrization of the failure mechanism, just by introducing, according with the upper bound limit analysis, a cylindrical hinge, which generates the collapse of the structure. Then we can just assemble the principle of the virtual works and solve it thanks to an optimization tool. In this case, I used Octopus, which is based on genetic algorithms. This is one of the preliminary results about this procedure. And as you can see, we are also trying to validate this procedure with some finite element analysis by using concrete damaged plasticity model available in Abacus. And as you can see, the results obtained by using the grasshopper tool, which is able to define the horizontal thrust and also the failure mechanism basically in no time, just in 5 seconds, is in perfect agreement with the result obtained in terms of damage pattern obtained by the finite element analysis. Okay, just some conclusions. I explained something about this novel digital procedure for the assessment of the masonry structure. And as you can see, the genetic algorithms are employed to explore different kind of collapse mechanisms, and we are also trying to apply this kind of approach for different structural typologies, like for example the dome. The proposed wizard script has been developed by using a grasshopper component, but we are working to develop just one single component, doc program in C#, in order to make this procedure as more user-friendly as possible. And our idea is also to share these components freely for other scholars and for other students, because I think that does not make sense our research if we cannot share it freely with other people. Thank you very much, Mislav. Thank you very much for this nice opportunity.
Marco, thank you very much for your very interesting presentation. I'm really satisfied with the things you're doing and you're presenting, and I hope you will continue in this good direction and will present even new results very soon. Thank you once again for the really nice presentation. And the next presenter is Anjali Mehrotra. She will present Stanford Heritage Project led by Professor Lorenzo, and I think 3 of you guys, Tassos, Nathanael, and Anjali will present the work you are doing. I must say that I was in Minho. I spent 2 months in Guimarães at the University of Minho this year, and these 3 guys were my roommate or next to me roommate. So we had really fruitful discussions about our work, and I'm really hoping for good presentations by Anjali. Anjali her resume is really impressive. She studied at Princeton, Cambridge, working at ETH Zurich for a little bit, and now is working at in Guimarães at the University of Minho. So Anjali, you can start.
All right, thanks Mislav for that really very nice introduction. And yeah, no, just thank you for having us here today. We're really excited to be presenting the project. Let me just share my screen.
Mm-hmm.
One sec, sorry, it seems to have disappeared. Sorry, one second. I need to share my screen, but I can't find it. Sorry, I'm having some technical difficulties.
Okay, no problem.
Yeah, for some reason I can't find the sharing option. It was just here, I'd just seen it.
Next to the mic is this sharing. Right, this one. No.
No, that's me.
Do you see it? This one.
Oh, there. Sorry, my bad. I had minimized the screen.
Okay.
Okay, there we go. All right.
Okay, we see it.
Okay, perfect. All right. Well, good morning, everyone. And Mislav, thank you so much for having us here today. I'm Anjali Mehrotra, and together with my colleagues Nathaniel and Anastasios or Tassos, we will be providing all of you with a brief overview of our project Stand for Heritage, where we focus on developing new standards for the seismic assessment of built cultural heritage. This project is funded by an ERC advanced grant and is currently being carried out at the Institute for Sustainability and Innovation in Structural Engineering at the University of Minho. So today's presentation is divided into 5 parts. We will first provide a brief introduction to the project and its overall objectives. Then we will provide an overview of the different work packages and some preliminary results. And finally, we will conclude with future directions of our research. But first, let me introduce you to the rest of our team. The coordinator or the PI of the project is Professor Paolo Lorenzo, who I assume most of you are already quite familiar with and probably doesn't need much of an introduction. The project currently has 3 postdoctoral fellows. There's Nathaniel, myself, and Anastasios. While Nathaniel focuses more on experimental testing, Tassos and I work on analytical and numerical modeling, respectively. We also have 2 PhD candidates working with us. There's Carla, who works with Nathaniel, and Yorgos, who works more with me and Tassos, as well as Luciano, who's our lab technician. Now, through Stand for Heritage, we are all working towards introducing formal standards for safeguarding built cultural heritage. Now, heritage buildings are intrinsically very diverse and complex, and are often subjected to earthquake-related threats such as out-of-plane damage to masonry walls, which is acknowledged as the main cause for loss of artistic assets and injuries to people both inside and outside buildings. But first, what is masonry? Well, as you can see, it's a composite material, which is typically made up of bricks, stones, or adobe, and it can either be mortared or dry stacked. In fact, it is a very old material and is represented almost everywhere, and makes up a substantial part of our built cultural heritage. Conservation of this cultural heritage is both part of our societal legacy as well as an important economic issue. In fact, in Europe alone, tourism to visit the many monuments and historical centers accounts for 10% of the GDP and 12% of the employment. Additionally, masonry represents 50% of the world building stock, and often older masonry structures need maintenance due to cracking, spalling, weathering settlements, or other causes of damage. Furthermore, masonry structures have traditionally only been designed for gravity loads. However, during earthquakes, brittle out-of-plane failure of masonry walls is a very commonly observed phenomenon. This is particularly relevant and necessary to address in several earthquake-prone countries in Europe, such as Italy, Croatia, Greece, Turkey, and Romania. There is thus a need to control out-of-plane displacements of masonry walls, the assessment of which is done using either simplified pushover analyses or more advanced numerical modeling simulations. However, this involves several challenges, as demonstrated by a recent blind prediction exercise whereby several international experts were invited to predict the seismic capacity of two U-shaped masonry specimens that were tested on a shaking table. The specimens comprised a more regularly arranged brick house and a more irregular stone house. 18 predictions were provided for their seismic capacities by the experts using different modeling approaches, and an enormous scatter was observed in the results. And in fact, there was a very strong deviation from the experimental response. Now, this scatter was linked in part to the numerical parameters assumed for these simulations, which was found to strongly influence the predictions. There is thus a need for integrated stochastic-based seismic modeling of these structures to better account for these uncertainties. Stand for Heritage addresses this need through 4 interwoven work packages. The first work package focuses on the characterization of the seismic signal, with the objective of identifying the ground motion characteristics most critical to the out-of-plane behavior of masonry walls. Specifically, given the shortage of real or historic earthquakes that exist, this work package uses stochastic analysis to create a huge database of seismic signals and to investigate their influence on out-of-plane behavior. These simulated earthquake records will then be used in an extensive experimental campaign, which brings us to our second work package, whereby tests will be conducted on rocking blocks, rocking masonry walls representative of facades, and U-shaped masonry wall assemblies. Specifically, tilting tests will be conducted to identify failure mechanisms, while varying parameters such as geometry, material properties, the presence and location of openings, as well as the quality of the connections to the transverse walls. Additionally, an extensive number of shake table tests will also be conducted to study the effect of the seismic input. The specimens to be tested include single and multiple rocking blocks, as well as U-shaped masonry walls. Furthermore, a 6-camera digital image correlation or DIC system will be used to monitor the displacements of these structures. In parallel, the third work package is devoted to advanced numerical and analytical modeling, with the results of these simulations being compared with the experimental tests. More specifically, rocking dynamics is used in MATLAB to formulate new analytical models to simulate the behavior of more complex masonry structures. Simultaneously, numerical finite element and discrete element models are being developed in both Abacus and 3DEC to better account for energy dissipation of the rocking structures at impact and to accurately reproduce the whole response history and model mechanism evolution over time. Finally, based on the results of the first 3 work packages, Work Package 4 provides guidelines for the design and assessment of masonry structures through the proposal of new seismic performance indicators and damage limit states. More specifically, this comprises the definition of performance indicators that are suitable for masonry structures, the formulation of damage limit states and fragility curves, the proposal of repair cost ratios for damaged components of masonry structures, and finally, the integration of the results into analytical and simplified tools for engineering practice. Over the past few months, our team has conducted both static and dynamic analyses of different masonry structures. From a static perspective, the team has focused on the design of tilting test equipment. The objective here is to experimentally identify different failure modes of masonry structures through the variation of parameters I mentioned earlier, such as specimen geometry, presence of openings, materials, and connectivity to transverse walls. Additionally, numerical modeling in DEM is also used to get an initial estimate of failure modes of different structural geometries, as well as the tilting angle required to cause collapse. Numerical modeling in both FEM and DEM is also used to model tilting tests from the literature, with the objective of also benchmarking the different modeling procedures. For a simple U-shaped wall, both procedures were found to compare reasonably well, correctly predicting both the experimentally observed failure mode as well as the collapse load multiplier to within 6% accuracy. The two modeling procedures were also found to very accurately reproduce the quasi-static response of more complex structural configurations, both in terms of geometry as well as boundary conditions. In terms of dynamic analyses, free rocking experiments were recently carried out in the lab using 5 blocks with dimensions of 20 by 10 by 5 centimeters. 20 tests, or 10 for each side, were conducted for each of the 5 rocking blocks. DIC analysis was then used to measure the energy dissipation and rocking amplitude with a high level of precision, while dynamic identification was used to measure the natural frequency and consequently to compute the interface stiffness. From a numerical perspective, the team has focused on reproducing this free rocking response using experimental results from the literature. The dynamic response of rocking blocks with varying aspect ratios was simulated in Abacus, while an investigation was also conducted into the effect of damping. In addition to free rocking, the blocks were also analyzed for the forced rocking response, and the 2 sets of results were found to compare remarkably well. Moving forward, the team will focus on the identification of ground motion parameters that are most critical to the out-of-plane behavior of these structures, as well as shaking table tests, where we move from single block rocking to multiple block rocking, and finally test U-shaped masonry structures. We will also work on the formulation of advanced numerical models to capture the nonlinear dynamic response of more complex mechanisms, and as well as conduct a bunch of fragility analyses in order to, with the objective of providing new performance indicators, damage limit states, as well as fragility curves. And finally, we will propose practical engineering tools to facilitate the seismic assessment of masonry structures. So with that, we would like to thank you for your attention, and would now be happy to answer any questions you might have.
Okay, thank you, Anjali, for an excellent presentation and the perfect timing. And I'm really hoping that Stanford Heritage Project will go beyond the regular knowledge we have about masonry structures. And I really hope that both universities, University of Zagreb and University of Minho, will continue to collaborate in future. From my personal perspective, I was really happy and to participate as a team group of you for at least 2 months. And once again, I want to thank you for everything you've done for me in Portugal. And I'm also sending some regards to Professor Lorenzo. And I'm also asking others if there's some questions about the project. If not, then we will continue to other presentation. Thank you, Anjali.
All right, no, thank you, Mislav.
Okay. Next presenter, if there is no questions, next presenter is Janko Košćak. He is from University of Zagreb and working in our laboratory. So, Janko, are you here?
Yes, I'm here.
Okay.
Can you hear me well?
Yes, I can hear you well. So, Janko is a PhD student at the University of Zagreb, dealing mainly with concrete, but he has a huge experience in experimental, both on-site and off-site laboratory experiments. So let's hope he will show us some really interesting material today. Janko, you can do it.
Okay, thank you. Can you see my screen?
Yes.
Yeah, okay. So hello to everyone. My name is Janko and I work at the Faculty of Civil Engineering in Zagreb within the Department of Engineering Mechanics as a part, as Mislav said, of Structural Testing Laboratory. Also, I am the part of ARES project as a member of the research group. Today, I will briefly present you our work regarding the testing of masonry structures. This presentation consists of 7 topics, starting with the introduction, followed by the 3 topics regarding testing of masonry structures. And furthermore, some advantages and disadvantages of such tests will be shown. And finally, I want to show you some test results of measured dynamic parameters obtained by the experimental model analysis within our laboratory. Of course, as stated a few times today, this year Zagreb was hit by a relatively strong earthquake and a significant number of buildings were damaged, most of which are masonry structures. Of course, this damage, as a cause for this damage, several reasons can be stated, such as structural non-maintenance, previously accumulated damage, and harmful interventions into the load-bearing walls. However, it is also a fact that these old masonry buildings were not designed to withstand such an earthquake intact. And in order to assess, retrofit and design such structures to be earthquake resistant, at least according to Eurocode 8, mechanical properties should be determined as accurately as possible through research and testing. On this slide, the determination of the in situ shear strength of masonry is shown, and before the testing, the plaster and mortar from the load-bearing wall should be removed. The test is performed at the longitudinally oriented brick, as shown in the figure, and the joints with some additional space from both sides of the tested brick should be cleared for the insertion of the hydraulic jack. This also needs to ensure that brick is not restrained on the opposite side of the hydraulic jack, and additionally, brick translation during the test can be measured with an LVDT sensor. Okay, pressure of the hydraulic jack should now be increased until the maximum value of force is attained. Right now, the brick is sliding along its horizontal joints without, of course, the pressure growth, and of course, the masonry shear strength, FVD in this expression, can now be calculated by dividing the maximum applied horizontal force measured. This is HU with a sum of upper and lower area of the tested brick. It's important to note that the value of shear strength measured with this simple test takes into the account the presence of the vertical load. Of course, because of existing vertical force within a tested wall, some normal compressive stress is acting on a tested brick, and in the combination with friction coefficient, it increases the value of a masonry shear strength. This can be seen from the expression. A value that is more useful in design is the joint shear strength without the influence of vertical load. This is FVM0. However, even with the simple shear test, the value of joint shear strength can be assessed if the value of friction coefficient is taken from the literature and if normal compressive stress is taken from a numerical model of a building. Additionally, a better information about the masonry shear strength could be obtained through the experimental determination of these parameters, and that can be done with the flat jacks. Here on this slide, measured values of masonry shear strength for two buildings are shown. On the left, average values for each floor of the Palace Hotel in Zagreb are shown. The values range from about 0.7 on the ground floor to about 0.3 megapascals measured on the highest floor. This is logical as normal compressive stress decreases with the building's height. The shear strength measured with a simple test also decreases. However, tests conducted on the building of the Ministry of Foreign and European Affairs, these results are shown on the right, show that this is not always the case, so additional measurements can be of great importance. This slide here shows the average test results of shear strength measurement for 20 different masonry buildings in the Zagreb, measured at over 150 locations. Each bar on the chart represents the average value of all measurements taken within the building labeled below, and yellow bars on the chart represents the measurements which were performed after the recent earthquake. Finally, the global average value of all tested buildings is 0.53 megapascals. Testing of brick compressive strength is shown next. In the laboratory, we performed this test according to European standard methods of test for masonry units, and according to the standard, A minimum number of tested specimens should be 6. The surfaces should be moistened and caped with mortar of at least 3 mm thick, and specimens should be stored for at least 14 days in controlled environment. Of course, the compressive strength is then calculated as the maximum load applied over the loaded area and should be expressed to the nearest 0.1 megapascal. This slide here shows the measured values of compressive strength for bricks taken from 14 masonry buildings across Zagreb. Each bar on the graph represents the average value for the building labeled below, and the global average value for all buildings is 30.1 megapascals. Next, the determination of mechanical properties of masonry walls with the usage of flat jacks is shown. The equipment needed for such tests is displayed on this slide. First and foremost, we of course need the flat jacks, and the flat jacks should be calibrated. Here, maybe I wish to note that we acquired the flat jacks recently, actually within the ARES project. So my personal experience regarding this test methods is limited, but our goal here is to expand our database with such tests. Apart from the flat jacks, steel shims are needed in order to compensate for the gap width between the slot and also to protect the flat jack from damage. Secondly, the slot cutting and cleaning equipment is needed, and strain measuring equipment is also necessary, such as LVDT or mechanical strain transducers, as well as the reference points which are attached to the wall. Finally, the flat jack has to be connected to the hydraulic pump equipped with the pressure meter. The summarized test procedure for various mechanical properties that can be obtained with the flat jacks are shown in advance. Firstly, in situ stress determination within the masonry is described here. The flat jack position of a width A should be marked on a selected masonry wall, and reference point for vertical distance measurement should be attached. At least 3 pairs of reference points should be placed as shown on the figure. The vertical distance between the reference points should be between 0.3 and 0.6 of a width A. Now the initial measurement at D0 can be performed. After the initial measurement, the cutting of the flat jack slot is conducted, and this procedure releases the normal pressure between the reference points, so the distance between them is now of course reduced. Now the flat jack should be inserted into the slot to compensate for the released pressure. The flat jack pressure is applied in increments until the distance between reference points attain the same value it had prior to the slot cutting. At this point, pressure of the flat jack B is taken, and the vertical normal stress can be calculated according to one of those expressions. So one can choose either a STM or real-time procedure depending about the calibration procedure. Secondly, in situ stress-strain relationship behavior or modulus of elasticity can also be determined using the flat jacks. The procedure is shown in advance. Firstly, 2 flat jacks of a width A should be placed into the horizontal masonry joints, one above the other, at the vertical distance of approximately 1 to 1.5 A. In addition, the space between the flat jacks should consist of at least 5 layers of bricks, also as shown in the figure, and the flat jacks should be connected to the same hydraulic pump. Secondly, LVDT sensors for continuous strain measurement are placed vertically between the flat jacks. Now the different levels of pressure should be applied in increments, and the pressure of each increment should be held for about 1 minute. At each increment, strains and pressure are measured, and the normal vertical stress is calculated. Finally, the tangent and secant modulus of elasticity can be determined by dividing the value of stress by corresponding strain value. Next slide describes the procedure for determining the masonry shear strength with flat jacks controlling normal compressive stress. The setup of the flat jacks is identical to the previously shown setup, but here the hydraulic pump and LVDT sensor are inserted between the flat jacks as shown in the figure. Again, this test setup for simple shear test is the same as previously described within the simple shear test. It is explained before that masonry shear strength accounting for the presence of vertical load can be easily determined. However, our goal here is to determine masonry shear strength without the influence of a vertical load, that is the joint shear strength, with the FVM0. In order to do that, we can apply multiple levels of pressure with a fledge X, for example, from P1 to P3. And for each level of applied pressure, shear tests should be conducted, and the maximum horizontal forces AG1 to AG3 should be taken. Now it's possible to calculate the masonry shear strength for each pressure level. This is FVD1 to 3. And also for each level of pressure, normal vertical stresses should be calculated. We can now plot the values of FVD on a vertical axis against the values of normal pressure on the horizontal axis, and the best fit straight line is now plotted through the given points. This is a red line on the figure. At the intersection of this line with the vertical axis, this intersection represents the pure joint shear strength at zero normal compressive stress. This is FVD0. Finally, it is clear from the figure that the inclination of a best fit line represents the friction coefficient. Lastly, regarding the flat jack, I want to mention some advantages and drawbacks of such tests. So regarding the disadvantages, it's sometimes hard to find an adequate place for testing due to local irregularities of masonry. Slots for inserting the flat jack are often cut with eccentric saws, which are using water, and that procedure saturates the mortar, so that's of course bad. Further, the uneven thickness of the flat jack slot can significantly affect the applied stress distribution. However, despite the mentioned drawbacks, valuable data can be gathered with such tests. And prior to the retrofitting of earthquake damaged buildings, it would be essential to make a number of such tests on rationally selected masonry buildings. The invested funds into the testing would be refunded through savings on renovation costs, as structural designers would enter the calculation with more realistic values of material properties. And the last thing I want to show you within this presentation is some test results regarding the dynamic parameters that we measured over the past few years within the earthquake rehabilitation study in the partnership with the city of Zagreb. So apart from the mechanical properties of material, dynamic parameters such as natural frequencies, model shapes, and damping ratios can be of a vital importance during the process of validation and calibration of a numerical model. This numerical model is of course used in the structural design. As a structural testing laboratory, we performed experimental model analysis on many buildings through the city of Zagreb, and some results will be shown in advance. This slide here shows experimentally obtained model shapes and natural frequencies of a concert hall, Vatroslav Lisinski in Zagreb. The dynamic parameters shown here were measured at a total of 112 and 20 degrees of freedom. Here the dynamic parameters of a Croatian National Theatre are shown. Again, parameters were measured at a total of 120 degrees of freedom. And because of the building's symmetry, measurement was conducted only at half of the building. Finally, this slide shows model shapes and natural frequencies of the main building of the University of Zagreb. Measurements were performed after the earthquake at the total of 192 degrees of freedom. And all of these on-field measurements of dynamic parameters are often used by our colleagues, structural designers, in a numerical models development process. And we're almost done. So finally, I stated some conclusions here on the last slide. So firstly, the test results obtained by testing of masonry structures allow designers to use more accurate input parameters within the calculation. Secondly, the results obtained by a simple shear test represent very useful information to the structural designer about the condition of the masonry. Third, the test methods with flat jacks provide the determination of valuable data on compressive stress coefficients of frictions and stress-strain relations of masonry. Then the systematic conduct of such tests would allow the establishment of a database that could be used for other similar buildings, and that would ultimately reduce the retrofitting costs. Further, the experimentally obtained dynamic parameters can be used to check the reliability of a numerical model, but also for its calibration, and last, by the comparison of measured dynamic parameters before and after the earthquake, or before and after the retrofit, a change in stiffness can be determined. We actually measured one building in Zagreb before and after the earthquake, and for same model shapes, the frequencies were changed, reduced. Okay, so that would be all. Thank you all for your attention. Thank you, Mislav.
Thank you, Janko, very much for your visually impressive presentation. I know it took you probably too much time for preparation of this. And once again, thank you for your presentation.
Yeah, no problem.
Okay, the next one is Dominic, so he will have a tough job to present after you. Dominic, are you here?
Can you hear me?
Yes. Okay. Dominic is fresh.
Just a second. Okay. Hi, everyone. Okay. Do you want to introduce me, Mislav?
Yes, just
okay. Introduce me.
Dominic is a fresh doctor. He just finished his PhD half a year ago, a little bit more, and he was the first one at our university who was doing this PhD defense online. So he knows how to do it, how to present online. He is not in the masonry field. He's working at the Department of Structures, but a chair for bridges. But his PhD and his work is oriented of some modern approaches and Bayesian updating and new analysis like value of information analysis. So both of us participated in one cost action, and as a result, he was very satisfied with the participation and implemented the knowledge from the cost action in his PhD. So today he will just show us a little bit about this new method of analysis, value of information analysis. And Dominic, yeah, you can start.
Okay, can you see my presentation? Yes. Okay. Okay, thank you very much, Mislav, for the introduction, and thank you for inviting me to do a presentation on this workshop. So as Mislav said, I'm working on the Department of Structures, but on chair for bridge engineering. And in my recently finished PhD thesis, I was dealing with the assessment of existing road bridges using additional information acquired with structural health monitoring. So my presentation is much different than the previous ones. So a lot of these presentations showed how you can acquire additional information on the material characteristics and on existing structures. Sorry, and I will try to quickly present you a method which can be used for quantification of these structural health monitoring information. So it is called value of information theory, and the method is called value of information analysis, and I used it in my PhD to quantify the economical feasibility of the structural health monitoring methods used on existing road bridges. It's the work here which I'm presenting and the whole algorithms were created mainly within the recently finished COST TU1402 action, which is called quantification of the structural health monitoring value. And my mentor, Professor Mandić Ivanković, he was a vice chair, and we actively participated in the action, and we developed for my PhD thesis an value of information algorithm, which can be with small modifications used to quantify any structural health monitoring information. So it's based on a value of information theory. It's developed in the late 60s, and it's been used in various fields of engineering, mainly first in mechanical and mechanical engineering for optimization of sensor placement on aeroplanes and etc. But it can also be used in structural engineering, and it basically, in simple terms, it gives us the answer: is the information we are about to acquire with structural health monitoring cost efficient or not? So, as you all know, you are all dealing with SHM in one way or another. In practical engineering, structural health monitoring is still not used in the extent it could be used, and this is often due to a conservative approach by some practical structural engineers who think that it's too expensive and that it is only feasible on landmark structures, so historic structures, landmark bridges, etc. The thing is that structural health monitoring can be cost effective on a variety of structures, but it needs to be selected and used properly. So using this value of information analysis, it is possible to define both: has the already obtained SHM information, is that information cost effective, and also it can be used for estimation of benefits and cost effectiveness of SHM before its implementation. So that are the two basic types of value of information. First one is posterior, which is conducted after the SHM information is obtained, and it, in simple terms, gives us the answer: was the money spent on SHM cost effective? So did we generate some benefits? And mainly benefits can be expressed with negative total costs. And the other pre-posterior analysis, which is really convenient, but it is also more complicated to use, can in some context give us the answer: will the money we are planning to spend on SHM information be cost effective? That one is pre-posterior is the basic theoretical framework of cost 1402, and it can be applied on various structures, but the thing is it's not so simple to use. There are certain parameters which are required. I will get to these in the end. I will now show you how beautiful and great that can be, but then we will come to the parameters, because as the value of information theory is based on Bayesian approach to probability, it can be really biased. So the final outcome is strongly dependent on the input information. In structural engineering, in all aspects of engineering, but also in structural, where the costs, we are dealing with large structures, and the costs of operation, maintenance, potential failure, closures of those structures are enormous. We have a lot of alternating outcomes. So, for example, we can estimate. For example, if we want to use various structural health monitoring methods, we can estimate and outcome based on the SHM we are using. In order to do that, very convenient method, graphical method, is called decision tree. It basically looks like this, but this is only for two outcomes, so it can have as many branches as there are SHM methods you want to quantify. So everything starts with the initial decision. The initial decision is oftenly decision made if we are talking about infrastructure. For example, in my field on bridges, initial decision is the one that the owner or the stakeholder is giving, so he can decide would he like to implement SHM or would he like to do, for example, an assessment without any additional information. That initial decision consequently leads us to the outcome, and that outcome is called prior outcome, and it is defined with total benefits. The problem in value of information is that you have to quantify everything with benefits. The easiest way is to quantify the benefits as negative total costs. So estimate maintenance, operational, assessment costs, and monetize them. And then it's really easy to compare the outcome when no additional information is used and when the SHM is implemented. Every branch has the final outcome, which is quantified by total costs, and then we can easily calculate the absolute and relative values of additional information. So the if we set up, for example, a decision tree, simple one like that, if we have one of the SHM methods that you presented today, we can define the outcomes in terms of benefits when it is used, this one, and when it is not used, and then based on the value, if the value will be negative, then we can say that implementation of that SHM method is not cost effective and it's not feasible, both from the perspective of the building owner and the building users. That is very convenient way to select the proper SHM methods that are used on our structures. Of course, it depends on the structures, depend on the assessment, etc. So we have these. They are called choice nodes, the square ones where you choose something, and the outcomes node. Those are probabilistically modeled nodes, which are result of input parameters I said before. So, for example, if we have an SHM, for example, flat jack, then what we need is so-called SHM outcome, which is defined as the likelihood of the analysis, and it's based on precision, device reliability, previous usage, etc. And that outcome leads us to another choice where we can choose to repair or not, or do not repair, or even to demolish and replace, etc. And then in the end, it leads us to the system states, which are again probabilistic node based on probabilities of failure. And we, in the end, we will get our outcome in terms of total benefits. So the easy thing to set up for value of information is to draw a decision tree, define as much SHM methods as we want. But the harder part is to define the outcomes or the likelihoods of the SHM and to monetize all benefits in terms of total negative costs. So this is the required parameters for the value of information analysis, and they can be they can be estimated with great precision if enough data is obtained. For example, probabilities of failure of initial structure can easily be, okay, maybe not so easily, but we are all structural engineers, so we can obtain the probability of failure with reliability analysis, and probabilities of failure are important for our final choice nodes. And the consequences of the, for example, structural closure, structural failure, total costs of SHM and operation and maintenance costs can be estimated because there are large number of papers out there for all types of structures, so they can be estimated, or also they can be estimated on the real experience. That was the in my PhD, I was estimating the costs based on previous experience from structural engineers and both literature review. So these two can be easily modeled if enough data is available. But the likelihoods and the outcomes of the structural health monitoring methods are the tricky one. So they need to be estimated with great precision because they directly they directly impact the final outcome. So for example, if we have a structural health monitoring method that we select, we need to be sure that, for example, if we are dealing with corrosion, and if it shows that there is indication of corrosion, we need to know how much, what are the probabilities that the corrosion is really there, and vice versa. So if it shows us that there are no indication of corrosion, we need to know what probability is that maybe there is corrosion. So that's why it is very dependent on the device precision and reliability, but also of post-processing of the data, because you can gather a large amounts of data, but it needs to be processed in the right way. If this step is done successfully, then the analysis should show with very large precision our estimation, will the SHM be cost effective or not. For example, I use it for, it can also be used for other things. I use it for assessment levels. So first level was done without any additional information, and then I was adding information from various SHM tools, and I was modeling in the final outcome. Will the boat structure owner, in my case it was the bridge owner, and the bridge users, is the implementation of SHM cost effective to them or not? Unfortunately, we don't have time for more. I know it sounds rather complicated, but there are many simple examples which can be used to present this more graphically, and then hopefully more of you would understand what I'm trying to explain. So that's all for me. Thank you for your attention, and thank you, Mislav, one more time for inviting me.
Okay, thank you, Dominic, for your presentation. I hope Josip Atalić, Professor Atalić, was also listening for this, and that this kind of approach we will try to implement in the process of assessment after the earthquake, because I think it can really help and to analyze cost-benefit analysis for our future really important buildings here in Zagreb. Okay, with this, I just wanna show, just a second. Okay, with this presentation from Dominic, it was the last presentation of today. Unfortunately, and it's a really pity that we didn't have opportunity to listen Javier Ortega from University of Minho. I was really happy to invite him to hold the presentation about non-destructive testing for structural analysis of heritage masonry buildings, building and urban scale, because he's also very experienced in the field of assessment, in the field of vernacular architecture. But we were experiencing some technical problems, and Javier was not able to participate at the meeting. But still, he will record, or he did already record his presentation, and tomorrow I will just put it somewhere in the schedule, maybe during the coffee break, or just move out the coffee break, and I will push it from my computer. So I hope, I'm sorry for Javier, I know that probably he is listening now, but he cannot share his screen. Once again, I apologize for the problems you experienced, but luckily we will still have this presentation. In the end, I want to also invite you for tomorrow meeting. The audience will be a little bit different because we will deal with timber engineering, and more or less with guys from timber engineering. So we will have several presentations about assessment of timber structures with just traditional methods and with new technologies. And we will have several presentations also from the guys from Slovenia, Sweden, and Italy, and two guys from design offices. So with this said, in the end, I want to, I don't know how to say my gratitude to all of you who participated in this meeting, and I'm really thankful that you were willing to hold the presentation. I know that sometimes it's still time consuming to prepare something, and I'm really happy that you managed to find some time. From the guys from University of Zagreb to all of the other guys who were preparing their work. I wish you all the best in your future work, and I think and I hope that all of us will collaborate somehow in the future. We here in today we did have a lot of presentations from University of Zagreb and presentation from University of Minho. So I must say that the guys at the University of Minho are from my point of view, the best ones in masonry engineering, the best ones in the world for sure in the masonry engineering. So we have a lot of, we at the University of Zagreb have a lot to learn from them, but also we have some knowledge and we can successfully collaborate in future. Once again, thank you everybody, and I hope we'll see you also tomorrow. There are also some guys who are just listening the presentation. They are not, they were not presenting today, and unfortunately we don't know who they are, but in the end there was around 40 participants today, and I know that there is also Professor Atalic who wanted to say something about the earthquake in Zagreb, but he was not able to participate because of other obligations, or he is also sending some regards. And in the end, I said this third time already, thank you everybody, and I hope these bad times and this COVID situation will end very soon, and that we will have opportunity to meet on a regular way. If somebody has something else to say, just speak now or be quiet. Thank you.